Started. I heard that you would like a break in the middle of the lecture, so I will ask you to raise your hand at some point after about 40 minutes if I haven't remembered to do that, or I'll ask the GSIs to remind me of that. But anyway, so where was I? I didn't get to see Aiden's lectures. I hear that everything went well, and I was off trying to figure out whether we could build an exaflop machine in 2021 with about 500 of my closest friends, and I came back with a terrible cold. But I think I'm mostly over it by now. So anyway, that's why I missed a couple of lectures here, but I'm happy to be back. And I first of all want to congratulate all of you on finishing homework 1. So give yourself a round of applause. Yes. I hope you learned a lot. I know that some people got very frustrated at various points in time, but hopefully it was still a good learning experience, and you learned a lot about how hard it is to actually get performance out of these machines, if nothing else. So what I'm going to talk about today, we're going to kind of pop back down the stack. So Aiden was talking about, at a fairly high level, where you find parallelism in a bunch of different scientific problems. And we're now going to kind of get to the more concrete level and talk about how do you program. And we're going to talk about how you program on shared memory, specifically OpenMP. And I'll say a little bit more about why OpenMP in a minute. And at the end, depending on how much time we have, I will also talk about some of the hardware that's underneath it, so you understand a little bit about what's going on there. So remember, we have our generic parallel machine that we're now talking about. So we no longer have a single memory hierarchy, which is what you were working with in homework 1. We got a bunch of processors, and we've got a bunch of memory, and they're connected together somehow. What we're going to look at today is when they're connected together and they can all access all of the memory roughly pretty quickly. Let's just say it that way. Not necessarily in all exactly the same amount of time, but they can directly access all the memory. Just to kind of remind you, and I showed a slide similar to this a couple weeks ago, but if you look at the top 500 list on what different kinds of machines look like architecturally, this has really influenced the way people write parallel software. And there's a thread actually that I haven't had a chance to answer on Piazza about why not use something elegant like Haskell or something, which might make it much easier to write parallel code. And so I'll say a little bit more about that as well. I guess the short answer is because we haven't been able to get performance, at least at scale, on the kinds of massively parallel machines that we're talking about over here on the right-hand side. Historically, there were shared memory machines that were relatively small. There were vector supercomputers. Those are kind of the oldest supercomputers. And then the vector supercomputers got a little bit larger in terms of parallelism. They put a few vector processors together into a machine, and that would be, these are some of the machines like the early, the Cray processor, so that dark blue hashed thing was a vector processor. And then there was a brief period of time when SIMD processors were all the rage, so that would be something like the MassPar machine. So these are little tiny processors that all did the same thing in parallel. It's a very elegant architectural model and a very elegant programming model that went with it, and we will talk a little bit more next time about a data parallel programming model, which you can think of as saying every array element has a different processor associated with it. That's kind of the mental model that you use. And there's some really cute algorithms that come up, which will influence algorithms that we'll use on machines today. But unfortunately, machines today don't look anything like that. They are, from a programming standpoint, there are going to be these clusters of very powerful nodes. And so as a result, we're going to separate into, how do you program the nodes, which tend to be shared memory, from how do you program the clusters. So the other thing that happened in the history that didn't show up in that single graphic is the rise of various kinds of accelerators. And this includes things like, well, most importantly, probably in here, the Xeon Phi, which is in Cori Phase 2. And by the way, I think 10 of you we got 10 solutions to the Homework 1 assignment with the extra credit problem of trying to do Cori Phase 2. We haven't had a chance to look in detail at how people did, but anyway, we'll show you some results from that later. And actually, they're not really accelerators as they're designed in Cori Phase 2 because it is the only processor on each one of the nodes. But nevertheless, the Xeon Phis for a long time were just attached onto kind of a real powerful CPU. But then the NVIDIA processors. And so, and then there's other kinds of accelerators that were little blips in here at various points in time. But the main point is that what we'll look at for a programming model for these is GPU programming. And we've invited John Owens, who has spent basically his whole research career doing GPU programming, to come and give a guest lecture on that, so you'll have a world expert on that. So anyway, what we're going to do in this class is not necessarily teach you about the most, yes, question.
I was wondering, is there any hardware difference between an accelerator and a GPU?
Normally, no, the way we use the terminology is accelerator is more a general term, and GPU is a specific kind of accelerator. So there's GPUs, and there were these Xeon Phis that were attached on. And so accelerator means you've got a CPU, a traditional processor, and then you attach something on the side, and they communicate usually through something called a PCI bus. So they send data back and forth between the two of them. So people a little bit abuse the terminology here. As I said, I don't think Xeon Phi, as it's in Cori right now, is really an accelerator. But anyway, that's the difference. Good question. So what do the parallel languages look like? So in this class, we're going to try to give you the most commonly used parallel languages for each of these different kinds of architectures, as opposed to maybe giving you the most elegant. In fact, I will say right up front, I am not a strong advocate for OpenMP. I've been arguing against it for many years, but nevertheless, I will do my best to tell you why it's great today. Okay, so let's see. As I said, you're going to see the most popular language in each category. And back when the supercomputers were vector machines, we programmed them with just annotations in the mostly Fortran at the time loops. Okay, so you had Fortran code, you had a loop, and you would put something like an IV-dep that says, vectorize this. There are no dependencies in the loop. Trust me on it. The compiler doesn't have to worry about it. All the iterations of the loop can be spread across a vector processor, which is kind of like a little tiny, you can think of it as having little tiny parallel processors inside of it as well. So, there's differences of opinions about whether that was a great programming model. The scientific user community actually, at least in retrospect, loved it, because although you did have to modify your code, and the compiler research community said, well, this was a complete failure because we couldn't automatically vectorize your code. There's lots of papers talking about how to vectorize it, but it wasn't in practice fully automatic. But the users liked it because there were very good tools that told them things like, here's a variable in the middle of this loop that is causing this loop not to vectorize, so go see if you can figure out how to fix that variable, and maybe you'll get much better performance. And that's something that you don't tend to get in the performance tools today. It doesn't kind of isolate and tell you, here's the problem in your code that's limiting performance. So people really liked it, at least when they saw the later things that were to come. And then there were, as I said, these SIMD machines, which were really tiny processors, a big kind of array processors, and much larger scale than a vector processor. And there were some beautiful languages, connection machine, Fortran, Star, Lisp, C Star, that came from a company called Connection Machines. And these were able to handle certain kinds of, certainly array computation. So you could just say add two arrays together by just saying A plus B. So that was really nice. And then you could do things like have sparse matrices. I think you heard a little bit about that kind of computation where you might have an irregular data access. You'd go out and get elements, variables from an array that were spread out at different indices. And you could do that also in these kind of languages by saying, here's an array of indices, go and load that from this vector, and it would get a bunch of different locations. But it couldn't really handle very irregular sorts of computational patterns, by which I mean you want to do divide and conquer, and you have some recursive algorithm, branch and bound search, adaptive meshes, which are hierarchies of meshes and things like that. So it was just harder to figure out how to squash those into a strictly data parallel model. So that was one problem. But the biggest problem really was they couldn't ever really get very good performance when they tried to map it onto clusters. And so when clusters took over, MPPs, massively parallel machines, or clusters, distributed memory machines, really took over in the architectural side, there was a lot of work to try to figure out, could we map these elegant data parallel languages onto them? Probably the biggest effort was in a language called HPF, High Performance Fortran, because of the use of Fortran in the scientific community. And a lot of effort went into trying to rewrite applications and trying to write the compiler. Unfortunately, people kind of ran out of patience. So was it actually an unsolvable problem? It's not entirely clear, but certainly for some of these irregular problems then it was both a problem of it couldn't really express some of the more complicated kind of algorithms that people wanted to have, and even for the more regular problems it didn't really get very good performance, and so people gave up on it. So then, we had shared memory machines that kind of came and went in different variations along the roadmap, with the most recent ones being multi-core processors. But even before that, we had shared memory multiprocessors. And in the kind of older version of it, the most common programming model was POSIX thread, so some kind of thread creation mechanism. And I will talk a little bit about that today, partially for historical reasons, although you won't be using that. We'll be focusing mostly on OpenMP, but it's useful to maybe understand a little bit about threads. And they had the same problem, which is people said, well, let's try to take these shared memory programs and map them onto a distributed memory cluster. So now think about what the compiler and the implementation has to do. You've got some program that's pretending to access shared variable, and you have to figure out how to divide up the variables across the cluster and then figure out how to introduce communication. And for an arbitrary program, that became basically impossible. So then there used to be, and I'm trying to remember the number, but like 40 different message passing libraries that were around after clusters became important. I don't remember if I'd mentioned that, but there was one, the chemistry community had their own message passing library and things like that. And then people said, this is insane, let's get together and at least figure out how to spell send and receive. And so that's where MPI, the message passing interface, came from. And it grew and grew because it turns out there's more than just send and receive, and it's a fairly complicated interface, which we'll talk about next time. And then when accelerators came on, there's things like OpenACC, CUDA, which tended to be, historically at least, the most, give you the best performance, at least on the NVIDIA processors, of course. So a lot of controversy about what's the right way to program these kinds of things. But in this class, we'll use CUDA, so that because you'll be running on NVIDIA GPUs, we'll use MPI, and we'll use OpenMP. And then the last thing you'll have a lecture on, also by an expert in it, is how to program in a cloud environment and the programming models that come up there. And maybe after that lecture, we'll come back and talk a little bit about why those programming models look different than the programming models that were developed for high-performance scientific computing. Okay, question? Yes?
I'm curious about why the user support did go down. It seems like if the goal of the compiler community was to make things more automatic, it seems like it would be easy to also have some automatic. And I know the Intel one had pretty good error messages in terms of what was going wrong, but there were lots of times where the vector report was just like, we didn't do it. And you're like, why? But what is there a technical reason, or was it more like they just didn't do it?
Yeah, so the question is there a technical reason that the compilers weren't very good at vectorizing or even providing feedback on what went wrong with your vectorization? Part of it is languages, and part of it is how much of the language you're using. If you're writing in Fortran 77 and you avoided things called common blocks, it's fairly easy for the compiler to figure out whether two arrays are alias to each other, and that makes it easier for the compiler then to figure out what's going on when it's vectorizing. If you're writing in C or C++ and you have, inheritance and you got pointers all over the place, then it's just impossible. So, yeah, so the problem got harder both because the programs got harder, the languages actually got, in some sense, more complicated and freer in terms of pointers, and the architectures got harder to compile for. So everything kind of worked against the compiler community. But everybody wanted the compiler community to just fix the problem. So anyway, was there another question? Okay, just stretching. Okay, so what we're going to do, we're going to talk a little bit about shared memory parallelism with threads. I know that Aiden talked a little bit about this as well, so mostly I'll remind you about that because it was over a week ago. And then we'll talk about OpenMP, what it is and why we're picking it, and then go into some details into OpenMP. And then talk a little bit about what goes on in shared memory hardware and why shared memory hardware isn't just the answer to parallel computing. So, okay, so here was our example from, I think that Aiden talked about, or I think I even talked about this one at the end of my lecture right before I left. So we've got our shared memory here, and we've got some variables such as an array and a shared variable, and you've got processors that also have some private memory. Well, I will often refer to this as the stack variables that are sitting here. So in a thread model, every time you declare a new variable, int I or whatever, that's going to go on the program stack, whereas if you say new or malloc or whatever, that goes in the heap, and those tend to be up here in the shared space. And exactly what happens with those will be a little different in different languages, but that's kind of just to give you an idea that those kind of local things that you're declaring are down here in the private space, and when you allocate something, it'll be up in the shared space explicitly. Okay, so what did it look like with threads, which are still around today and are still used for systems level programming and things like that? And the standard here, also that came out after people have been programming with threads for a long time, is the POSIX standard. And pthreads, then, as they're called, which is the POSIX threading interface. So these are system-level calls to be able to create parallelism and also to synchronize between parallelism. And it was defined as an interface to make it easy to, across at least Unix-like environments, and with this POSIX standard, then to make it easy to write portable code. Because there again, there were a few different threading models that different vendors had in their own operating systems. And so what do we have in a pthread model? Support for creating parallelism, synchronizing parallelism, parallelism. And you didn't really need any kind of explicit communication in these models because you're just going to have shared variables, and just reading and writing the shared variables is going to be enough. You'll have to synchronize them. So this is what it looks like, and this is maybe partly motivation for why OpenMP came into being. So here's pthread create. It takes a thread pointer and a thread attribute and a function, which is the void star star void star thing, and then the argument that's going to be passed into the function. Okay, so these are all the different pieces into it. So you're going to need later to be able to stop a thread or wait for a thread to complete, and so you give it a handle, and that's the thread ID. And then there's some attributes that you can pass into it to tell it kind of how to execute various things that are kind of details of the how you want it to run. Okay, but you're going to fork or going to create a thread, and that thread is going to run a function, and so you pass in a function and whatever argument that you want to pass into that function, and then there's some error code that will get returned from the create in case the thread can't even be created. Okay, so here's a little example of a Hello World program, and you would compile this. You need to make sure you're compiling it with the right flags. I actually was starting to put in exactly how NERSC has the different flags set for OpenMP, but it turns out that I decided for consistency reasons not to put the exact details in here, but there's going to be some kind of a flag to make sure that you're able to compile with pthreads. And then so you've got this Hello World program, and here you've got the pthread create that is creating just this say hello function. It's going to spawn off a copy of this say hello function and pass in nothing to it, nulls. Okay, and then so we can fork it off 16 times, and it will run. It will run 16 copies of this, and it's going to print out Hello World 16 times with, and hopefully you'll get actually 16 different lines that say Hello World, but there's no other real information that you'll get, and you don't know which one will print out first. Okay. In this case, I haven't put in a number that says, in the Hello World which thread it is that's printing out, but if you were to put in a number, it wouldn't necessarily come out in any given order because the prints are happening in arbitrary orders. Okay, so that's kind of ugly, and so there's, and especially when you want to do something with loops, and other problems come up. So in a lot of scientific code, as you heard about, you're going to be looping over big data structures like arrays, and you want to have parallelism across those. So you could have a multi-dimensional array, my stuff, that's an n by n array, and you want to do some work on every element of the array in parallel. So here would be a simple way to write this in a relatively simple way, at least in using pthreads, would be to spawn off a thread for every element of the array. Okay? So the problem with this is it's terribly slow because pthread create is a fairly expensive thing to call. It's a system level, operating system level call, and even though people have done a lot of work to try to make them faster, you can't usually do this unless you've got a huge amount of computing that you're going to do inside of that update cell. The update cell thing. You're not going to be able to you're not going to be able to amortize the cost of the pthread create. And so that says, well, you better do something else. And so people will, when you're writing pthread programs, you'll divide it into chunks, and you'll have a loop that'll, you'll strip mine your loops. You'll have an outermost loop that maybe only goes up to 16, and have one pthread create inside of that, and then have the finer grained work inside of there, and have to manage the indices yourself. Okay, so. But you're trying to basically also divide up the work evenly, and it also means that when you're trying to divide up the work evenly, you have to manage the bookkeeping of figuring out exactly how many things are in the n by n array, and just make sure you get all the index arithmetic right and don't leave any of the elements out and stuff like that. Okay, the next problem that comes up in thread programming, which you also saw, I believe, was a race condition, right? So in a race condition, you have a shared variable, in this case s, and we've got two threads. I haven't worried about how you program it in this particular case, and they're both trying to write to s, and in this case, they both read into some register so they can do the addition, because all arithmetic is done in values that are sitting in registers. So you read something into a register, they both could read the same value of s, they both add to it, they both write it back, and one of the updates gets lost. Okay, so that's an example of a race condition. In general, we will have race conditions, also called data races, whenever two threads are trying to access the same variable and at least one of them is doing a write. In this case, we have both a read and a write that both of them are doing. The reads conflict with the writes conflict with the writes. But you can see if they're both trying to write something, depending on who wins, you'll get a different answer. So that would be one kind of race condition. If you have one processor doing a read and the other processor doing a write, the problem is, does the read happen before or after the write, and you'll get different behaviors. So anytime you've got two processors trying to access, or two threads trying to access the same variable, at least one of them is doing a write, you're going to have non-determinism. You're going to have behavior that will depend on exactly the order, and that'll be a race condition. And so we can fix this with things called locks. And in pthreads we have mutexes. And so a lock is going to be a special kind of variable. And the operations on it, acquire and release, are things that are guaranteed even if two processors are trying to do it at the same time. The underlying implementation will make sure that only one of them succeeds in acquiring a lock. And then when you release it, that another thread can go ahead and acquire the lock. And so as long as anytime you have these kind of race conditions in your program, you protect it, then you should be able to at least prevent the particular race condition, although exactly what values they get back at a different point in time, depending on where you've locked things, can still give you some kind of odd undetermined behavior in your program. So this will prevent, the locks will prevent the case where both of them try to read the same shared variable, they both try to write it back, and one of them gets lost. And so in this case, for this particular, that particular example, a lock would be just fine, because it would guarantee that we don't know which one will get there first, but one of them will get there first. It will read the value, it will increment it, or add something to it, write it back, release the lock, and then the other one will come in. And so, assuming a plus is associative, which it is on integers, or maybe close enough in floating point, we'll get the same answer independent of which way they run. But it won't force a particular order of execution. Okay. And we have some other problems that come up with locks, and that is sometimes you need more than one lock because you have more than one data structure. So you have data structure A and data structure B, and you have lock A and lock B. And if you've got two different threads, and this comes up a lot for those of you who've studied databases and things like that, are very familiar with this problem. If you've got one thread that acquires lock A, and then acquires lock B, and thread 2 tries to acquire lock B, well, let's say that both thread 1 succeeds in acquiring A, and thread 2 succeeds in acquiring B, but neither one of them then can acquire the other one, so they both just stop. They both hang, and so that's a deadlock. Okay, so that results because there's sort of a cycle in the order in which everybody is trying to acquire the locks, and so there's ways of getting around that. But this becomes stuff that most programmers don't really want to worry about very much. And so you're trying to define a programming model that it's not going to make all these problems go away, but it will make it easier to write programs that don't have these problems. I guess that's the easiest way to say it. Okay, so these POSIX threads are these operating system level features. It was nice because you could use them. You can use them from multiple languages, and it's very easy to share data because you could just have these shared variables. Some of the pitfalls that I just talked about are that the overhead of thread creation can be pretty high. You can't just put a thread creation in every loop, or you'll completely overwhelm the system by starting too many threads. You should think about the idea that a thread is going to have a pretty hefty piece of state associated with it, and so you'll also run out of memory, and then your system will get really slow because it's trying to run all of these threads, and you only have a finite number of processors. You still have you've got these data races that are nasty, and if you ever have a bug in your program that appears sometimes but doesn't appear every time you run the program, likely it's a data race of some kind. Okay, so not guaranteed, but most likely that's probably what you're seeing, is something where something is just happening in a different order, and so sometimes it runs just fine and sometimes it doesn't. So you need to look for data races. You can also have data races down in other pieces of the system software too, but hopefully you won't see any of those. There's things called transactional memory, and I won't talk about those in this class, but ideas for making it easier to deal with these kinds of shared variable programs. And instead we'll talk about OpenMP, which is the most commonly used shared memory programming model in the scientific computing community. Okay, so and it's actually pretty commonly used even outside of scientific computing when you want to program on shared memory. And it's going to help with some of these problems. It doesn't make them go away. It's not going to make race conditions go away. It might make it easier to avoid, for example, loop overhead by providing built-in constructs that, for loops that will help you manage that and kind of give you some rules of thumb for avoiding some of these problems. So just for kind of your background, there's a few different ways in general of creating parallelism across different parallel languages. So if you were to look at something like Silk, you would see this future construct. What we saw here is in pthreads is something like a fork construct, and there is a feature in OpenMP that's also like the co-begin construct. So co-begin, co-end says I have some section of code and they've got a few different things in it, in this case 2, and those different things will run in parallel. So it's pretty structured. So the nice thing about a co-begin, a co-end, in this case, is that it's got a co-end on it. So you kind of know in the code when the parallelism is done because you fall at the bottom of that block. Unlike a fork join sort of construct where you spawn a thread and you've got a thread ID, and at any point in the program somebody can go and join on that thread, and that will wait for that thread to complete. And so you can write much more complicated sorts of parallelism patterns using fork and join because they don't have to be nicely nested like this, but you can also cause yourself a lot of confusion by writing very complicated programs using fork and join with thread IDs that get handled in some odd place. Now, future was an idea originally in a language called Common Lisp. I believe that was the first place. Actually, I think it was a version of Scheme where it first came up. But anyway, so these were in functional sorts of languages, and the idea was to say, I've got some variable and I want to use a function to go off and compute the value of that variable, and I'll wrap this thing called a future around it. So it's very much like a fork statement. It says go off and run this job in parallel, and the rest of the program can continue running. But there's sort of some hidden synchronization inside of here that says if I suddenly need the value of v, if I have it there on the right hand side where I need to read the value of v, well, that thread may not have finished yet, and so that statement will automatically hang or kind of stall until the point that that thread is completed its job 1 and comes back with the value. This can also be really a nice way of programming, but it's also somewhat limited in terms of the kinds of synchronization patterns you can have, and it can be somewhat confusing in terms of what is happening with your performance. But there's lots of great papers if you want to read about futures in various languages. Okay, so I think I've said all of these sorts of things. Any questions about those? Okay, so, oops.
Are you going to talk about what you don't like about OpenMP at some point?
Yeah,
Okay.
I think it'll become obvious. Right. Okay, actually, maybe not entirely. There's another question, yeah.
So when you do the future, when you do, I guess, any other of these things, when you want to access V again, is the memory going to be managed in such a way that the computer knows where it is?
Yeah, the way to think about it is change the computer hardware. Oh, the question is, thank you. The question was, the first question, by the way, the previous question was, am I going to tell you what I don't like about OpenMP? So I'll make sure I do that later. The question just now was, if you access V multiple times, will it remember that it knows the value of V, essentially? And yes, the way to think about it is, and the idea actually came from an architectural idea that with every variable, every memory location, actually, you would put a little tag in memory that said whether or not that variable had been filled in yet. And so when you spawn this task off, it starts some thread and it's running and it knows when it finishes, it needs to write the result back in that location and set the tag bit to positive. And then anytime you access it after that, that will continue working. You can see why futures are maybe not so popular today because we don't have that kind of tagged hardware, and so then trying to figure out how to implement that without the tags and hardware became complicated. There is a very closely related construct that I tend to call promises. I think a lot of people, in my opinion, abuse the notation and call them futures, where where the type that gets returned here is called a boxed up or a promise type. And so you can't actually just put V inside of a statement here. You have to say kind of open or unbox or acquire or whatever V, and then in the program text you have two different types, the kind of the boxed up one and the unboxed up one. And then every time you accessed V, you would have to say unbox it. But what you would probably do is the first time you access it, you would put it into an unboxed variable, and then you would after that use that one. But yes.
No, is that what Scala does?
I think it does. And does anybody else? I'm actually not a Scala expert, although I should be. I think it might have promises. Promises are pretty popular, and I think it does make it a lot easier if you can implement this. Kind of the idea of futures much more easily if you keep the types separate. Yeah, I'd have to confirm myself. Okay. So what is OpenMP? It stands for the Open Specification for Multiprocessing. OpenMP.org is the standard place to get this. It is the motivation was because it was sort of awkward to program in these threaded just using something like p-threads. And especially for scientific computing that had a lot of loop-level parallelism, they wanted to put some things in there that was easier for people to parallelize those kinds of programs. The specification is controlled by something called the ARB, the Architecture Review Board. So it's a nonprofit organization. It's a little bit, you have to kind of get into the club and pay your dues and go to the meetings and stuff if you want to influence the spec. It is an ongoing activity. There's a lot of big companies that are involved in that because they're trying to make sure that OpenMP is something that will run on their hardware. So the latest spec was actually done in November 2015. It's called OpenMP 4.5. They are working on OpenMP 5. I will actually talk about things that are basically up to OpenMP 2 dot whatever, and not 3 or 4 or 5. I'll say a little bit more about what's in 3 and 4. There's some stuff in 4 that you might find useful, but at this point, some of the implementations of some of the stuff in 4 it's not clear how well it's implemented across different machines. Okay, so let's see. What is OpenMP? Well, it's got 3 different kinds of things in it. It's got preprocessor or compiler directives, and these will look like hash pragma things that are sitting in the middle of the code, and it'll be hash pragma OpenMP and some other stuff here. There can also be library calls, and so you have to include the OpenMP library in the top of your OpenMP program using some kind of syntax like that, and then you can call those functions. And then there will be environment variables. These are usually things that are all caps, so they're easier to kind of separate, and you'll put them in. I meant to change that from srun to what is it called, sbatch? Is that what anyway, whatever your submission thing is these days. And so you'll put them into something like your scripts, or whenever even if you're running your OpenMP on a laptop, it'll be something about your environment that will set some of these kinds of variables. So those are the 3 main pieces of it. So from a programmer's perspective, what you're going to get is a portable, threaded, shared memory programming environment with a fairly light syntax. And this is where I would say my biases will show up. I think when you start adding all the features that you need to get performance, then it starts to get less light and less elegant. And I also, as a programming language person myself, researcher, I kind of object fundamentally to the idea that you stick a pragma into a program and change its semantics very fundamentally, that you have a sequential program, you stick this pragma OpenMP keyword into it, and it completely changes how the program runs. So that's just sort of a, that's kind of a, I don't know, elitist programming language person perspective, but anyway, that's what it is. Okay, so it's going to allow you to separate serial regions and parallel regions, and that's another thing that I find a little frustrating, is that I think it's too easy to write serial regions in OpenMP code, and mostly if you're programming on even a 64-core node or a 32-core node, you want to be thinking about running everything in parallel unless you absolutely cannot figure out a way to run it serially if you want to get performance out of it. It's going to give you some constructs, and it's going to hide some of the details of how the implementation, the runtime system, the program stacks for all these different threads get managed. It's not going to parallelize your code automatically. It's not going to guarantee that you get speed ups. You will find many times that your first parallel program may run slower than your serial program, and it's not going to actually free you from data races, although there's some simple rules that will keep you out of trouble, and if you can follow those rules, then you can probably avoid data races, but it doesn't prevent them. I should say, I thought I had this earlier in the slide, but there's a great tutorial online, and I stole a couple of the images from Tim Mattson and Larry Meadows at Intel, and I think at the end of my slides there's definitely a link to where that tutorial is. That was a day-long tutorial. What's that?
It's in the beginning too.
It's the beginning. Okay, thanks. There's a day-long tutorial, so I couldn't squash all of that into an hour-and-a-half lecture. But it goes through more. It gives you little assignments to do and things like that. So if you feel like you're a little bit lost in what OpenMP does before you start the homework assignment, feel free to go and try out some of those examples and read some more details. It'll talk more about OpenMP 3 as well. So, but what does this stack look like? You've got your hardware down here, and we should think of it as having shared memory. They call shared address space, so the processors can read and write the same variables that are sitting there in memory. You've got some operating system that would have things like the pthread fork kind of construct that I talked about before. And built on top of that will be an OpenMP runtime layer, which will manage, you can start more threads and things like that than are actually started at the operating system layer. It'll keep track of those. And it'll also keep track of things like synchronization inside of this runtime layer. And so the three pieces that I talked about earlier, there's the compiler directives. So there is something that happens when you translate the OpenMP code into machine level code, and it looks at those pragmas and does something different than if you were just compiling it for a serial machine. Hopefully if you ignored those things, your program should work as a serial program. But depending on what you write in there, it could cause something to behave differently. And you've got your library calls that you can make from your programs, and then your environment variables that might they'll affect things like how much parallelism. You can control how many threads are at a maximum OpenMP has. You can control that both in the library, with the library calls, and also with the environment variables. So you've got an application that you've written, for example, that uses all of these things, and then somebody who's using your application that you've written for some scientific calculation or whatever, they may just affect the environment variables by running the program in a different kind of environment. Okay, there's also a great, I called it sort of a cheat sheet. It's a list of all of the things that are in OpenMP 4. And actually all the 4.0 things are marked with a clear 4.0. These are some of the most commonly used things that have pragmas for parallelism and pragmas for parallel loops, and things to ask for the number of threads, and atomics and locks and things like that. Okay, but you can see the full list of it there. It's, I think, about 3 pages. So maybe you want to print it out when you're doing your homework assignment. Keep it with you. Read it at night, whatever. Okay, let's see. So we'll do Hello World in OpenMP, starting with just Hello World in serial C. So we're going to just have this, the Hello World program that's going to print out an int, which in this case is 0, so a really boring program. So how do I change that into a parallel program? Well, it's pretty simple. I can add include the OpenMP library. I will add a pragma parallel that says I want to execute the next block of code in parallel, and then I can ask for then each one. This is going to be running multiple copies of this code. Each one of them will have its own thread number associated with it, and you can ask what thread number this particular one is by calling the OMP get thread num, and then when you do the print, you'll print out both Hello World and the ID that it's coming from. So, any questions about that?
Does this like give you any control over, like it could do 3 and like reuse the threads as they finish, or it could do 16 or whatever? Like, does it give you any indication of what it's planning to do, or?
So the question was, does this give you any indication of what it's planning to do with how much parallelism it's going to kind of use and things like that? So the environment variables and some other things you'll see will control how much parallelism are there. It has a default that it'll look at what the system is and says, oh, there's 16 cores, I'll probably use 16 threads. And so, I mean, that's why also to me it's a little odd, which is when you run this, you'll get completely different behavior depending on how many threads you run it on. It's not part of the program. But anyway, that's just kind of the way it is. And there's going to be some other things for trying to control how you use the cores and things like that. Marquita?
There, so you might request a number of threads in a variable before or inside your parallel pragma, but you always want to call this OpenMP get thread number because it may or may not provide you that number of threads. So if you, for example, ask for 32 and your system has 16 cores, there are circumstances under which it'll give you only 16 cores. Threads.
Thank you. So the system may override your hint. They're considered hints when you give them, and I'll show you how to give hints before. So you do need to compile this with an OpenMP compiler flag. That it makes it clear that it can use these kinds of constructs. And then OpenMP set num threads, this is what Marquita is saying. This is saying, I would like 4 threads. And it may say, well, you don't have 4 threads, so you're not getting 4 threads, but that's what you're asking for. And then you've got this parallel loop. So in this case, assuming that it's actually running with 4 threads, what you're going to get printed out is, hello world from 0, hello world from 3, hello world from 1, hello world from 2, in some arbitrary order. And the print statement itself is written in such a way in these OpenMP environments that it won't like scramble the characters together or anything like that, but it will print out in arbitrary order. Okay, questions? Okay, so let's see, a little bit more on parallel regions in OpenMP. So that's what I just said about getting the different printouts. So what can go inside of a parallel construct? When you said parallel there, the thing that's used across a lot of OpenMP is what's called a structured block. So what you can put inside one of these parallel regions is a structured block, and it's a block of one or more statements inside of it that has one endpoint coming in and one entry point and one exit point in the program, except that you can also have an exit in the middle of it, which will cause it to drop to the bottom. So, and this is, so it should be something that looks like kind of a block of code where you don't have things sort of jumping out of that region of code or something in arbitrary ways, but it can fall to the bottom of it, it can't jump out. And so most other parallel OpenMP constructs will also use this notion of a structured block. You can also nest parallel regions, and this shows a little picture from Tim and Larry's tutorial that shows these threads being created and destroyed as you go in and out of parallel blocks. And it doesn't mean that necessarily every time you go into a parallel block it's the same. Maybe you gave a different hint the first time, said I want 4. The system has 6, and so it gave you 6 the second time because you didn't override that somehow. And you can also nest them. So inside of one of these parallel threads you can have another parallel block. So things can get, but you will want to be a little bit careful, just as you would have with P threads, although these may be lighter weight than P threads. You probably don't want to start 1,000 threads if you've only got 16 cores, because you're going to end up running really slowly. There's one thread here that's marked in red, and that's called the master thread, and that sort of persists both in the serial regions and then when you go into the parallel regions as one of the threads. So you kind of always have this one master thread, and when you say parallel something, it kind of goes off and runs one of the pieces, and the other P-1 things are run on new threads that are created and destroyed. For those of you who are worried about operating systems and threads, you may be worried about creating and destroying threads. OpenMP tries to keep them around in between so you don't have too much overhead. Yes?
The master thread is like one thread throughout the entire program. Is it always the same ID, or can that change between different things and within a nested parallelism loop?
I believe it's always thread ID, thread 0, but yeah, so I think that it'll always be thread 0 as you go inside and out of these blocks. So yeah, the question was whether it was special. Okay, so are there, what about shared variables? What happens with these? In general, kind of the default is going to be that all the threads can see the same variables, but there will be different kind of rules and different ways of controlling that I'll talk about. So that's kind of useful. You can have a big, huge data structure, and everybody can read and write to it, so you can get all kinds of useful work done together, but it also means it can be really dangerous because of race conditions. So here's a little example with a shared array in OpenMP. So we've got an array that's declared, array X that's declared as a 100-element array. You've got an OpenMP parallel loop, and so what happens is that you can think of that thread 0 as declaring that array X, so it's got a big chunk of memory. You go into a parallel loop, and maybe you call some function. Whoops, I renamed it helper and foo. So it should be called foo in the code over there, because I couldn't fit helper in the boxes. So it's calling that with some ID, which happens to be the thread ID, and the entire array X. Okay, so you should think of this as it passes in a pointer to that array, that whole chunk of 100 elements, but it's got an ID. So inside of that foo or helper function, you could imagine that it's trying to, it will have some calculation that said, oh, if I'm thread 0, execute elements 0 through 24, and if I'm thread 1, do whatever. So multiply the thread ID times 25 and kind of access those elements of the array so that you would avoid any race conditions. So you would all be accessing different elements of the array. But it's kind of up to you. You can do that this way using this kind of a parallel construct. And this would have just these 4 fixed threads. We also call this at least sometimes called this SPIMD parallelism, so single program multiple data parallelism. It's sort of a static amount of parallelism. You think of it as taking the code and making P copies of it for whatever your processor is, and then running those pieces of the code, those blocks of code in parallel. And then when you get to the bottom, there's an implicit synchronization or barrier synchronization before the print happens that only one thread will do that print statement, and it will only print when all the threads have completed running their pieces of the code. Oh, yes.
So is there a way to set, let each thread have a copy of X so that they would not have race conditions?
Yes, so there will be a way of giving each thread a copy of X. That'll be called a private variable, but in this case you're going to get, these are, by default, this is going to be a shared variable. It'll be a shared X. Yeah. That'll be pretty expensive, by the way, to make a complete copy of X unless it's really what you want. Okay, so let's see. I think maybe this is a good time to take a short break. What did you do, 5 minutes? Stand up and stretch? You didn't do it. Oh, I see. It was requested. Okay, everybody just stand up in your chairs, stretch around a little bit, and if anybody really needs to take a break outside, do that, but we'll try to start in another 3 minutes or so.
Congratulations.
In what?
For the National Academy.
What?
There must be something online. Did you see this?
No.
Is this the acronym what I think it is?
Yeah. Thank you.
Big.
Yes, thank you.
You got the first person. Congratulations. Excellent.
Thank you.
I thought they used to call people yes. You're just learning from the mail.
Only the Nobel Prize. You don't get the- All right, let's go ahead and restart. I don't know if that was 3 minutes. I wasn't really timing it. All right, so let's see. So you can get loops to work that way, but hopefully you got a sense that if you tried to write a program this way, then as with p-threads, you kind of have to manage the question of which threads are handling which parts of the array yourself and keep the indices straight and make sure you don't leave, have an off by one error that leaves some element uncomputed or whatever, something like that. So there's an easier way to do this in OpenMP. And this is really the most elegant, I think, part of OpenMP is the parallel looping construct. And so what we're going to say is, for the most part, a parallel looping construct, if it doesn't have any loop carried dependencies, and I don't know that, did you talk about loop carried dependencies, Aiden? I don't think you did. Okay, so loop carried dependency, you can think of it, since we've talked about a race condition, would be if you tried to run all of those iterations of the loop in parallel, there would be a race condition. So another way to look at it, a loop carried dependency says that the thing that you do in loop iteration 7 depends on something you did in iteration 6 or one of the lower ones. So for example, if you're reading x in one iteration and writing x, the same variable, either over and over again, or you read it once, you write a sub 1 and then you read a sub 1 in the next iteration, you'd have a loop carried dependence. So anytime you've got to read, you've got an access to the same variable, at least one of them is a write, you have a loop carried dependence. Okay? So we'll say, well, let's assume we don't have any loop carried dependencies, which means all the iterations are independent. They can run in parallel and nothing bad will happen. And that will make it really easy to write some kind of a parallel loop. And so The nice thing is that the preprocessor and the runtime system figure out kind of how to break up your loop. So here you've got a simple loop that just goes from 0 up to 25. You don't have to worry about whether you've got 4 cores or 8 cores, and as long as you don't have any loop carried dependencies, this will work fine in parallel. And you also don't have to worry that the runtime system is going to create 25 threads and manage 25 threads. So it will divide up the iteration into some reasonable number of blocks, and the pragma here that you're using is OpenMP parallel 4. So there's a 4 there that's all tied together, and then you put a for loop right after it. And by the way, you do need to be a little careful about your line breaks, because these pragma things are on a single line, so sometimes you'll see things with slashes that mean the line is kind of logically continued, but the thing right after it is going to be the for loop. And so this will be a nice way of parallelizing a simple loop where there's nothing bad that will happen when you run the iterations in parallel, and it will execute those in parallel. Okay, any question about that? All right, so now you may say, well, what do I want to do with this parallel loop? Depending on what it's doing, I may want different kinds of ways of dividing up the work. So you may want to, for example, statically divide it up into maximum size chunks. So the compiler can look at, and the runtime system can look at how big the loop bound is. So in this case, it was 25. And it can say, well, I'm going to run on 5 threads, so I will give each one exactly 5 iterations of the loop, and it'll manage the fact that the i's have to be different in there, so they'll all get different versions of I, and so you don't have to worry about the details. It will also worry about the fact if you're running on 4 threads, you've got 25 iterations, it doesn't evenly divide, it'll try to spread them out as evenly as possible, and you don't have to worry about kind of that bookkeeping as well. Okay, so that would be what we call static scheduling, and it will statically divide up whatever iterations you have into equal numbers of pieces, and there's an optional argument that you can get when you designate that you want it to use static scheduling, which is a clause that goes right after the for in the pragma. You can say that it should be divided up statically with a certain chunk size. So maybe you want to say, oh, there's something special about my computation, and I really want it to divide it up into 2-element chunks, because there's lots of stuff that happens in between A0 and A1, not so much between A1 and A2. And so I'll divide it up in statically and say, divide up in these chunks, and then it'll get wrapped around round robin so that every processor, so that all of the chunks get used. Okay? So that's still static, though, because it just depends on how many things you have to do. You can also say that I want it to be dynamically allocated, and so what this is going to do is it's also going to have some fixed number of threads that it's running on, but it's going to kind of divide up the iterations of the loop dynamically. This is really useful if you have some iterations are really expensive and some iterations are really cheap. So for example, let's say that your loop body says, if I'm something that is not a simple expression like even or odd, but I've got some little conditional that says if that conditional is true, then execute this big huge piece of code, and otherwise just go to the next iteration of the loop. So it'd be bad if you did static scheduling of that, because some processors could get lots and lots of big pieces of work, and some of them can get all the little pieces of work, and you would leave processors idle. So dynamic, what it will do is it will put the work logically into some kind of a queue, and it'll just then keep scheduling iterations of the loop and until all of the iterations have been done. And once again, you can give it a chunk size that says don't put one iteration at a time in the queue, but kind of divide it up into chunks of 2 or 4 or whatever you want. Then the last one is what's called guided. It's a short name for guided self-scheduling, which is an idea that was developed when people were doing a lot of research on how to parallelize these various kinds of loops and compilers. And this one also does it dynamically, but the chunk size is going to be changed over the execution of the loop. Anybody idea why would you want to exponentially decrease the size of the chunk size? Or work gets done. So the answer is at the beginning, you kind of assume things are pretty well load balanced. You may not be able to predict exactly how long every iteration is. You give out big chunks of work because you have plenty of time to worry about the fact that at some point some of the processors may be behind and some of them may be ahead. And at the end of the iteration, you're really trying to get them all to finish at the same time. So you want little pieces of work so they can kind of fill in all of the little gaps that might exist between the different pieces of work. And I think what you're probably getting at is you want the big pieces at the beginning because there's still some overhead of scheduling a chunk of work, and so you want to maximize the size of that when you can, but you don't want it to be too large at the very end, because that could give you a really uneven finish time. Yes.
So the chunk, are you talking about work? Like, is it similar to work?
warp in CUDA?
Yeah.
Now I need a CUDA expert to tell me if warp is similar to, I don't think so. I think that that's why we're having John Owens come to talk about CUDA. But the question is whether warp is similar to chunk. Just think of this as you're giving a hint, and that's all it is, to the compiler and the runtime system for OpenMP that says, I've got this loop, it goes from 1 to 1,000,000, divide it up into chunks, and I might give it a hint that says, give me a chunk size of 100, but if you say guided, it will start maybe at 100 and get smaller closer to the end, so that you'll have smaller pieces. I think warp is a more static notion than guided, but that's okay. Okay, so what about these shared variables? I gave you one example where you had a shared array. Let me just fill this in. But the question was also, does every thread get its own copy of the variables, or do they get, or they all share the copies of the variables? And across different programming languages, you have these sort of different notions. When I showed you the picture before, I said things that you do malloc and free on are typically up there in the shared space. Things that are just like loop iteration variables, those will tend to be private, because each one, you'll want each processor, each thread to have its own loop index, right? Because it's going to be indexing a different part of the array. So in OpenMP, you can declare variables as either shared or private. And this is where I would say OpenMP starts to not look so simple anymore, because you really do have to think at a pretty high level which variables are shared and which variables are private. And there are rules for the defaults. So let's just go through the example first. So we've got our OpenMP parallel block that we want to execute, and inside of this block, so we've got this code that's going to execute in parallel. We've got a private variable temp, which was declared out here, but we're going to say it's going to be a private variable. So each thread will have its own copy of temp, and we could have thread ID is also one per thread, which is important because that's the thread number that they're going to use to figure out, for example, what to do inside of foo. And then you've got our big data structure, and we don't want to make a copy of that every time we come in and out of the threads, because it's sitting there in shared memory space, and our shared memory hardware is supposed to make it possible to access all the elements of the array. And so the big data you're going to make shared, and the other things you'll make private. And so this is the way that you can control which things get copied, you have separate copies of for every thread, and which ones are shared by all the threads. Okay, is that clear? Aiden.
Was there a default? I thought big data, I don't need to say anything about it. And it was
Right. So the default is shared, I believe, for
it's declared outside the loop.
right. So I'll say something about the defaults here, and there's still there's a question about these automatic variables, right? So what are the defaults for shared versus private? And then I'll have a little editorial comment at the end. So shared, most variables in a shared memory programming model are going to be shared by default. So that's kind of the model that OpenMP uses. So that's why things will tend to be shared by default. And specifically, there's global variables that are going to be some things like common blocks in Fortran, or static, file scope variables in C, and anything that you allocate with new. So that's consistent with what I said before about just your mental picture. Think that the things that you allocate as with new or with malloc are going to sit up there in the shared region, and that is what will happen with those by default as well. And they are, and that's also true with static. So if you have something declared at the file scope in C. So the things that are stack variables, so if you're inside of a function and you declare a new variable, and those are typically that are inside of a parallel region, those are going to be private. So if you declare new variables inside of your parallel region, each processor is getting a copy of those new variables that you declare inside the parallel region. And so all these automatic variables, let's see, these stack variables are the automatic variables. Okay, so my bottom line is you should say which things you want to have private and which things you want to have shared. There are some differences across languages, and even if you can remember the defaults and are very carefully using the defaults, it's really helpful to anybody who picks up your code later if you've said which things are private and which things are shared, because otherwise it can be really confusing. Okay, is that, other than saying it's really confusing, declare everything explicitly? Are there any questions? Okay. Okay, one other common thing that comes up, I told you so far, just don't write programs that have race conditions across, that don't have any loop carried dependencies, and then they won't have any race condition. But there's something that you often want to do in the body of a loop, which is to say add up all of the things in the loop, or in this case we're computing an average. So here's a little piece of code which is just going up from I equals 0 up to max minus 1, and averaging some elements of an array A. And so you can parallelize that thing by putting a pragma OpenMP parallel for in front of that for loop, and that will give you a for loop. But this has a loop carried dependency. It's got a race condition in it. Every loop iteration is accessing both as a read and a write the av variable. You're going to get complete nonsense if you don't put this other stuff here. So what you do is you say reduction, and that says I'm going to have a special kind of variable. It's not private and it's not shared. It's a special reduction variable, and it's the av variable. So there's the name of it. It was declared outside, so I know what it is. And what am I going to do a reduction? I'm going to do reduction using the plus operator. Okay? And so what happens is OpenMP knows what reduction means. It means I'm going to do a bunch of things with an associative operator. It has an identity value associated with it, 0 for plus, because I can add 0 to anything and get it back. And so it will correctly produce code that does what you want in this case, which is producing the average of all the elements. It'll sum up all the elements in the loop, and then at the last statement, one thread, which is executing at the bottom of that loop, is going to execute, will compute the division and compute the average. Okay? And so, let's see. The way to think of this in a little bit more detail is each thread is going to get its own copy of that variable av. It's going to be initialized to 0 in this case because 0 is the identity for plus. It's going to let it run the iterations of the loop with each of those independent copies, and then when it's all done, it'll add them all together with using that plus operator that you told it to use. And so you could also write complete nonsense in here where you're putting a multiply up there and you told it to use a plus for the reduction, and you're not necessarily going to get anything sensible. But if you do something sensible and use the same operator for the reduction that you're using in the loop, you'll probably be adding up all of the variables. And so you get the original, you'll put it back then in the original global variable. So there's a whole bunch of reductions. I just copied this from Tim and Larry because it was too much to put on my to try to reproduce it. So this just tells you what the different operators are and then their initial values and stuff like that. Okay, so there's a bunch of different things you can use for. Yes.
I may be confused with this, but that seems like you're making a lot of separate threads, so you have a lot of overhead of creating threads. You're doing a really simple mathematical operation.
Right, so the question was, aren't you creating a lot of separate threads for a really simple mathematical operation? One of the nice things about OpenMP, though, is I didn't say how many parallel threads are being created, right? So OpenMP actually will do something reasonable in this case. If you only got 4 cores, it'll divide that loop by default into static chunks of size max over 4 with the right rounding to get the last 4 elements or 3 elements or whatever in their place, and it'll only create, say, 4 threads.
In fact, just to add, it actually has internal default parameters about what is the shortest loop it can parallelize. If it's just over 10, max is 10, you'll see that it's not going to parallelize this at all.
So I'll just repeat that. What Aiden was saying is that OpenMP also has some internals in the implementation that say if the max value here is only 10 and you're running on a really big machine, it might not parallelize it at all because it knows there's just not enough work. Even on a small machine, there's just not enough work to justify starting up even 2 threads to do 10 iterations of that or 5 iterations on each of those parallel loops. Thanks. Okay, so there's a bunch of other things you can do reductions with. Now, you might need to do something more than just a reduction, and now you have to really worry about regular synchronization. And synchronization in OpenMP is going to look similar to what we saw in pthreads or what you see in any other language. You'll have some kind of locks, or actually what they're called critical regions. And so you can say pragma OpenMP critical, and then the code that's running there will run serially. So only one thread will be in that critical region at a time, even though that whole block of code can be nested inside of a parallel loop. There's also OpenMP barrier, which says I've got all these threads that I started, and I want to just wait at this point for all of them to get to this point in the code, and so they'll all sit there and wait on that barrier. And then you can also do explicit locking. So you can have, these are now function calls, so OpenMP set lock, an OpenMP unset lock, and you can put some code in there. And so this is useful if you have, for example, different data structures with different locks. You don't want to just say it's one critical region that will prevent every thread from going into that critical region. You could say, well, one thread can go into this kind of critical region over here for data structure A, as long as this one is going into a different critical region for a different data structure B. You'll associate different locks with them, and you can make that work as well. And you can also say, this is kind of like, well, okay, not quite like a barrier. You can also say that there's a region inside of a parallel piece of code that I want to make single. Now, you could also write this by just ending your parallel region of code and coming back out of it into the serial region and then going back into a parallel one later. But sometimes that can be awkward. Like if you're in the middle of a parallel loop and you want to say, here's a little serial region of code, for example, a print statement, and I only want one thread to print it out, then you could put it in there. But you could also do that with a critical region. Okay. So here's a simple little benchmark that looks like, I think, things that Aiden talked about when you're trying to do some kind of parallelism over a structured grid. So you've just got a two-dimensional mesh and a two-dimensional array, and we're going to just average with our nearest neighbors. So I haven't written the code out here, but just imagine that for every grid point x and y, I'm going to look at, say, x minus 1 and x plus 1 and y minus 1 and y plus 1 and so on. Okay, and so what do I want to do to parallelize this loop? I'm going to, first of all, there's an outermost loop which is iterating over time steps, and then there's an innermost loop which is running over the grid. But I can have one parallel OpenMP4 that is going to operate on these two loops, and it'll parallelize. It'll kind of figure out how to divide those loops up into the proper number of threads depending on how much hardware you have, and then it declares some of the variables, the grids, as shared, and then there's some local variables. Each thread will have its own copy of there for computing things like the loop bounds and stuff like that. Okay, and all right, and there's there's a synchronization at the bottom that you don't have to put in there because it'll just fall off the bottom of the parallel region of code. And then what we do on every iteration, and I have a feeling I'm missing a curly brace for the next iteration of the loop.
Yeah.
But yeah.
The T steps, I think that brace is...
I think that brace should be down here below this, right, exactly. That's what I'm thinking too. I didn't count the curly braces, but thank you. If you counted them, yeah, it looks like that third curly brace should be down at the bottom. So I'm just using 2 copies of the grid. Why am I doing that? Because I'm guaranteeing that every time I go, when I'm in the iterations of the loop, there's only one thread ever writing any particular value of the grid. So any x and y, there's only one thread that's going to be, one iteration that's writing to grid sub x, y. And then I'm going to have a temp grid that I'll use. I guess I maybe need to show more of the code here on the right-hand side. I'll use another grid for the right-hand side so that everybody can be reading from that, and they can be reading from the same locations, but that doesn't cause a race condition because it's all reads. And so I'll read from one grid right to the other and then flip them at the bottom of the loop. Okay, so there's what's happening to my, it's not animated the way I thought. Okay, so if I put different kinds of scheduling clauses on my loop, my parallel OpenMP4 loop pragma, I can get different kind of schedules. So for example, I could say it's dynamic and it's going to go over the rows of the array, which is the outermost loop, and it'll dynamically hand those out to different threads. Okay, I could say static, which says I want to go row by row across the entire thing and divide it into chunks. So that will give me, say if I have 4 threads, it'll give me something that looks like this. I can also say that I want to divide it into squares, and so this is going to be a little bit harder to write, but I can modify my each thread is going to traverse a square of this, so I have to rewrite my code more here. This is not just a simple annotation, and then I'm going to, and then there's also going to be a pthreads version, so I'm going to just show you some performance numbers for comparison. Okay, so those are all OpenMP, and the last one is pthreads. So this is running on an old machine. I actually don't remember which machine it is at this point, but it was running on up to 16 processors. And here's the dynamic, static, squares, and pthreads version. They're all scaling pretty well. This is a large ocean. It's a 2050 by 2050 ocean. So there's enough work in actually all of these different implementations that it scales pretty well. You can see squares scales a little bit better. You're getting, this is speed up. So you're getting better speed up from squares, and well, not quite as good, but pretty close to the same speed up from the pthread version, which is also using a similar kind of decomposition of the data. And so let's see. So that doesn't look too bad. It says that in OpenMP we can do this kind of scheduling pretty well, and it gives you, pretty close to perfect speed up. And if you use a smaller ocean though, so this is now only 258 by 258, and by the way, I should point out that the previous speed up went up to 16. So these speed ups, the maximum speed up was over 14 for the best case. Now I'm going to change the axis so it only goes up to 9. So these speed ups are much worse, and this is because it's a smaller grid. So now you see the overhead of the parallelism of both of the models. And actually, pthreads does a lot worse than 16. In fact, the overhead of parallelism for starting up pthreads makes it worse than only using 8 threads, because it's just too expensive to do that when the chunks of work are too small. You'll also see that in this squares case, we get a negative speed up for one and one thread. So that's an important thing for all of you to remember, that when you're computing a speed up, if you're ever showing speed ups, to be clear what you're using as your baseline for the speed up. In this case, what we're using for the baseline of the speed up was the serial code, the serial implementation that didn't have any OpenMP in it. And it turned out that the OpenMP version, for whatever reason, even running with one thread, had a little bit of overhead and it slowed it down. And sometimes you'll find the best version is the parallel version running on one thread, and sometimes you'll find it's the serial code. But it's just very important whenever you're producing speed up numbers to say what the speed up is relative to. So you can see, though, that you need to use the right kind of decomposition to give you the locality that you want to so that you're mostly working on blocks, so that you have your up and down neighbors all in the same block. Okay, so given that it's shared memory hardware, it may not be clear why would it be any faster to access this square than it is to access a stripe that looks like this. Okay, and to understand that, you do need to understand a little bit about what's going on in the hardware. So let's see, I think we kind of talked about this. In general, the OpenMP scaled pretty well, and the compiler generated code compared pretty well to the handwritten code, and you saw a couple of different ways of doing scheduling, both dynamic and static, and OpenMP generally worked pretty well. This is a pretty simple problem, and the loop level of parallelism that's in OpenMP, we wrote the program in such a way that we didn't have any race conditions, we didn't have any loop carried dependencies, and then OpenMP is actually a really convenient tool for parallelizing that kind of a loop. When you have a much more complicated program, it may be harder to figure out how to put it in the OpenMP model. Okay, so just briefly, what's going on underneath the hood? Why are you seeing somewhat different behavior in terms of the performance by running across stripes than you are from running across squares? And the answer is what you learned very thoroughly in homework 1, which is all about locality in the memory hierarchy. Okay, so let's just review. We've got our shared memory architecture that has our P processors, and they're somehow connected into a memory. And you can think of this as a bus, although I think I'd also talked about the fact that it may be something a little bit more sophisticated, a little mesh or whatever, something inside of here. So where are the caches in this case? Well, at least some of the caches you're going to put right next to the processor, because you want the data, remember, to be really close to the processor so that you can access it really quickly. And so you'll have an architecture that looks like this. There may also be caches on the other side of the bus, but on the other side of the whatever that interconnect is between the processors. But we'll just worry for right now about the caches that are sitting up here really close to the processor. Say the L1 caches, they may actually be physically sitting on the processor die, that L1 cache. Okay, so we want really high performance from our memory system, but we also want really high performance for the case where the data is sitting in our cache. So remember, that's why we had the caches in the first place. And there's a few different policies the caches can use. It can use what's called a write back policy, which is I'm going to write my data into the, if I'm making modifications, I'll write it into the cache, and I'll wait until I'm completely done with that value, until it gets kicked out of the cache, to write it back to memory. I can also do what's called writing it through, that says at the point that I first write it, I will write it in the cache, and I can access that new value, but I'll write it at the same time, push a value out to the memory so that other processors can see it. But the basic problem is now we could have potentially 2 copies of the same variable. And you could say, well, I shouldn't have 2 copies of the same variable if I didn't write a program with race conditions. Well, first of all, you have to be a little careful about what that means, but in terms of when you kind of flush things out of your cache. But the problem is you don't have any control over what's over in the hardware, right? So what's in the hardware can be causing problems for you, even though you didn't say I wanted to necessarily make a cached copy of this particular variable. So you have the kind of normal mechanisms doing load and store operations, but that's going to load things in the cache. And the first problem to see is cache coherence. That is, if both processor 1 and processor n have loaded the same variable and they start modifying it, how do you keep the 2 copies consistent? So here's a variable u, which starts out as the value 5. Sorry, the colors here are a little bad. And that gets loaded into 2 caches. I think this is pretty obvious. Now, one of them decides to write a value 7, on top of u, and the other one, it doesn't see the 7, and it does a read, and it still says the old value of 5, and the other one also can see a value of 5, and it can go off and get it from processor 1. So even after this third event, when processor 3 wrote a value 7 into u, it didn't propagate down here to memory. And even if it propagated down to memory using something like write through, it didn't propagate up to that other cache. Okay, so now we've got kind of garbage that's happening in the middle of the implementation. So what you do is you run what's called a cache coherence protocol, and basically all the processors will listen to everything that's happening on the bus and try to figure out if any of the transactions that other processors are doing are affecting things that are sitting in their cache. So if someone else is doing a write, and you'll put a notification on that, processor 3 notifies that it's writing to you, and then processor 1 will see, oh, I have a copy of you, I need to throw it out, get a new copy, something like that. Okay, and so that sounds like a somewhat complicated way to fix the problem, and it is, but you can get these protocols to run, and that's exactly what shared memory hardware does, is it runs some kind of a protocol like this, and there's a whole literature of different variations. I'm sure some of you are very familiar with all of it, but you don't need to worry about it in this class except to understand that there is a bunch of complexity there to make sure that all the processors are seeing the same version of the variables in memory. And what this means to you is that it's really hard to build a shared memory machine after about 100 cores. Maybe a couple hundred, maybe 64, maybe we can debate about exactly where the number is, but at some point the cache coherence logic, because remember they're all listening to this wire, if you will, in here, or even if it's a more complicated data structure, somehow they all have to keep track of what everyone else is doing, and that becomes very complicated and very hard to scale to large number of processors. There are ways in which people scale this up to larger machines. So it's called directories. So they might have physically distributed hardware in which they keep track of what all the different copies are in different caches that are sitting around in the system. And I think the main thing that I want to say is that you really want to have this model that says that when you write a variable, that everybody else will see the same version of that variable that you just wrote. And so what does that mean when all these processors are executing things in parallel? I mean, we don't really know what time anything happens. And it's true, if you write a program with race conditions, exactly who writes first may not be clear. And so the intuitive model, and this is due to Leslie Lamport, is called sequential consistency. And what it says is your program should behave as if only one processor takes a step at any given point of time. Okay, so that is the answer that it gets is the same as if there's no parallelism, but it can get any possible interleaving where P0 takes a few steps, and then let's see, P1 takes a few steps, and then P0 again, and then P2, and then P1, and then P3, or whatever. And so they're all accessing the same shared variables, but it should look as if only one of them is taking a step at any given point in time. And that step would be something like a load and store operation, but you shouldn't see the case where one of them has done a load and a store, and now somebody else sees sees some stale value of it happening, because you wouldn't get sequential consistency. And I think rather than going into some of the details of memory consistency models, there's one other thing that I wanted to talk about here. Where is it? Right, I wanted to talk about sharing. So the other thing that you need to know when you're worried about performance programming is there's true sharing. We've worried about that. It's called, you see race conditions, you can get the wrong answer and so on. But now we've carefully written our loops in such a way that P0 is going to work on the first chunk and period 1 is going to work on the second chunk. So there's no race conditions, and so there's no true sharing in your program. So true sharing is when you've got two processors or two threads trying to access the same variables or the same locations in the array. Unfortunately, because of the way hardware works, you can also see something called false sharing. So remember that when you load something into the cache, because the processor is trying to amortize the cost of getting something from fairly slow memory, it's going to assume that you have some good spatial locality. So rather than just loading one word, even if you only access one word, it's going to say, I'm going to guess that if you're going to access this word, you're going to access, say, the next 3 or 8 or whatever words, and it'll load a chunk of them into your cache. And so now the problem is, even if you've written your program very carefully in such a way that you're not accessing the same variables, you can have a cache line that has a copy in both processor 0 and processor 1. Processor 0 over here is only accessing the first element, processor 1 is only accessing the third element or whatever, and that cache line kind of has to go back and forth between that bus in order to make sure that you keep consistent copies of things. And the hardware will make sure that happens, but it will cause your program to run slowly. So bottom line, it's another reason why you may want to pad or something like that, to make sure that you don't have things that are chopped across cache lines. If you've got some variables that you're going to access very frequently from arrays, and you allocate them all in one big shared array, and every thread is accessing its own element, most likely you're going to end up with false sharing in that data structure. No race conditions, every thread has its own element, but lots of false sharing. Okay, any questions about that? Okay, so let me just leave the, I think I'm completely out of time, but I wanted to give you the references. So just to point out that you can look online, you can find the links for a number of different tutorials. There are a number of other shared memory programming languages. As I said, Silk is one that has really nice theoretical properties and so on. There's some popular ones coming out of some of the other DOE labs, Kokos and Raja, but we'll use OpenMP in here. And the good thing is that once you've learned one of them, it'll be pretty easy to pick up the others. Okay, thanks very much.
One announcement. During the class, we just learned that Katya has been elected to the National Academy of Engineering, so now you can congratulate her.
Thanks, I learned too.
Homework 2 is out too.
Beat me to it. I was about to announce.